Have you ever wondered what would happen if you could drill a hole straight through the center of the Earth and just jump in? Where would you end up? Would you pop out on the other side? Say, in the middle of the Indian Ocean, if you started in North America? It sounds like a simple question, but the physics behind this hypothetical journey is absolutely mind-blowing. So let's grab our imaginary super drill, put on our heat-proof suits, and take the ultimate plunge into the heart of our planet. First, let's set up our experiment. We need a tunnel, a perfectly straight one that goes from one point on the Earth's surface through the very center and out the exact opposite side, also known as the antipode. For this to work, we have to make a few massive assumptions. First, we need to completely ignore air resistance. We'll imagine our tunnel is a perfect vacuum. Why? Because if it weren't, the air pressure becomes so immense as you fell deeper that it would crush you long before you got anywhere near the core. Not to mention, the friction from falling at incredible speeds would instantly incinerate you. So, no air, got it. Second, we have to deal with the Earth's rotation. Our planet is spinning at about 1,670 kilometers per hour at the equator. If you just jumped into a hole, you'd carry that sideways momentum with you. You wouldn't fall straight down. You'd immediately slam into the side of the tunnel and, well, it wouldn't be a very long trip. So for our thought experiment, we'll pretend the Earth has stopped spinning. Or maybe our tunnel is magically aligned perfectly with the axis of rotation, going from the North Pole to the South Pole. That works too. And the final, biggest assumption, we need our tunnel to be indestructible. It has to withstand unbelievable pressure and temperatures that are hotter than the surface of the sun. The Earth's core is a scorching 6,000 degrees Celsius, or about 10,800 degrees Fahrenheit. Without a miraculously strong, perfectly insulated tunnel, you and the tunnel itself would be vaporized. So we'll imagine it's lined with some sci-fi material we'll call unobtainium. Alright, our perfect, vacuum-sealed, non-spinning, unobtainium-lined tunnel is ready. You're standing at the edge. You take a deep breath and you jump. For the first few moments, it feels just like skydiving. You're accelerating downwards at 9.8 meters per second squared, the familiar pull of gravity. But as you fall deeper, something strange starts to happen. You continue to gain speed, but your acceleration starts to decrease. Why? Because gravity pulls you towards the center of mass. As you fall into the Earth, more and more of the planet's mass is now above you. That mass is actually pulling you up, back towards the surface you just left. Think of it like this. When you're on the surface, the entire mass of the Earth is beneath your feet, pulling you down. But once you're, say, 1,000 kilometers inside, the shell of Earth that's now above you exerts its own gravitational pull, partially canceling out the pull from the mass below you. The net gravitational force pulling you toward the center gets weaker and weaker the closer you get. Despite the decreasing acceleration, your speed is still building up to truly astonishing levels. You'd break the sound barrier within minutes. Your velocity would keep climbing, faster and faster, as you plunge through the Earth's crust and into the mantle. You'd be traveling faster than a rifled bullet, then faster than our fastest jets. By the time you reach the outer edge of the Earth's core, about 2,900 kilometers down, you'd be screaming through the void at your maximum speed, a staggering 28,000 kilometers per hour, or about 17,500 miles per hour. That is fast enough to circle the entire planet at the equator in about an hour and a half. At this point, you're halfway to the center. The gravitational pull from the mass above you is becoming significant, slowing your acceleration, but your momentum is immense. You'd zoom past the boundary into the core, and then at the exact center of the Earth, a truly bizarre moment occurs. You've traveled 6,371 kilometers straight down. At this precise point, the mass of the Earth is distributed perfectly and evenly all around you. The gravitational pull from every direction cancels out completely. For an instant, you would be perfectly weightless, just floating, but you wouldn't stop. You're traveling at over 28,000 kilometers per hour. Remember? Your momentum carries you right through the center and into the other half of the planet. Now, the journey reverses. As you shoot past the center, the net gravitational force is now pulling you back towards it. You are now technically falling up. This force acts as a brake. Your incredible speed begins to decrease, but at the exact same rate at which it built up on the first half of your trip. You're decelerating, but you're still moving incredibly fast. You rocket through the other side of the core, into the mantle, and back up towards the crust. Your speed bleeds off, slowing from thousands of kilometers per hour, back down to hundreds, and then finally, just as you reach the surface on the exact opposite side of the planet, your speed hits zero. The entire journey, from one side of the Earth to the other, would take approximately 42 minutes. It's a fascinating number that comes from the physics of gravity and oscillation. You'd arrive at your destination, floating weightlessly for a split second at the mouth of the tunnel on the far side of the world. But wait, if you don't grab onto the edge, what happens next? You guessed it, gravity takes over again, and you immediately start falling back into the hole, beginning the entire 42-minute journey all over again, in reverse. You would oscillate back and forth, from one side of the Earth to the other, like a human pendulum swinging through the planet's core, forever. A perfect, perpetual motion machine. Now, let's get a little more realistic. We can't really ignore goes down about 12.2 kilometers. That's less than 0.2% of the way to the center. The pressure and heat at that depth were already monumental. Going thousands of kilometers deeper is simply not possible with any known material. Then there's the issue of the Earth's core itself. The outer core is a sphere of molten iron and nickel. Even if you could build a tunnel through it, the immense pressure would try to collapse it, and the heat would melt it. The inner core, while solid, is still under unfathomable pressure. But as a thought experiment, it's a beautiful illustration of the fundamental forces that govern our world. It shows us how gravity isn't just a force pulling us down, but a force that pulls everything towards a common center. It transforms a simple fall into a magnificent, cosmic oscillation. So, while you might not be booking a ticket for the 42-minute Transplanetary Express anytime soon, the next time you drop something, you can imagine it's not just falling to the floor, it's trying to start its own impossible journey to the center of the Earth. What wild what-if ideas do you have? Love this journey? Hit that like button and subscribe for more science fun.